Hi everyone, in this video we're going to address noise in the context of this ill-posedness that we showed in the previous video. So just as a review, this is what we constructed our forward operator to be, and its inverse, we showed that it was a diagonal in the eigenbasis. So all we do is we invert those coefficients. These coefficients alpha n are the eigenvalues, and they decrease rapidly. They decrease exponentially, and this was the PDE we were solving. And so we showed that if I perturb, I can make an arbitrarily small perturbation in my data and get an arbitrarily large answer difference in the model parameter given a small perturbation for fixed perturbation size epsilon. And so just to formalize this in the context of noise here, let's say that I give you that the data is true data plus some noise eta. And we were to naively invert this, where we use phi to just be the inverse of f. Now f inverse is a linear operator, so this is m true plus f inverse acting on eta. And so this tells me that my error E is m minus m true is the sum n equals 1 to infinity of eta dotted into Vn 1 over alpha n of t Vn. So this was our error term, and this was the source of our instability. So, how unstable are we in practice? Well, it all depends on what these coefficients look like. And if all these coefficients are 0 or approximately 0 in the sense of they're let's say they're much less than alpha n of t for large n, then in fact we're fine. But actually, in practice, this won't be the case. These will actually dominate whatever coefficients actually come out in the true data. And the reason why is because you typically think of noise, right? You have an instrument, say you have a Gaussian distribution, noise typically is it bounces all over the place, right? If that's your noise eta. But then as you increase, so the low frequency modes in this basis, these are sine waves, that's one low frequency mode. There's another relatively low frequency mode. But now, if I let's take a bright yellow to just make it really obvious. But now, if I take a super high frequency mode, sine of, 10 million pi over L, then the dot product of eta with Vn is significant. And so overall, this term, the dot product over alpha n of t, is huge. And this leads to large error. So in fact, what we showed last time is actually yeah, sure, you could say, well, Tyler, that's abstract, sure, it's discontinuous, but what if these coefficients are small? Well, in practice, this intuition says that they won't be small, that in fact the high frequency modes will actually tend to have pretty large inner product with the noise, possibly more than our actual data. And so this will actually lead to large error in practice as well, not just theoretically. And so what we'll discuss in the next video is, what if I don't use if I don't directly invert the system? What if I use phi tilde to be approximately F inverse in a way that sort of zeroes out or damps, or yeah, let's say damps, because you could just zero them out. That damps the large modes with large N, or the high frequency modes. And so that's what we'll discuss in the next video. And this is basically how we are going to address this issue of ill-posedness, is basically to just say, okay, well, you know what? This is unfortunate. We can't exactly recover the solution because of this issue, but since the noise will be matching these high frequency modes, most of the signal is going to be in these low frequency modes anyway. So let's just essentially give up on the high frequency modes because they're going to make our solution much worse than if we somehow damp them out. And because it's essentially we can't get the exact solution out. And so that's what we'll discuss in the next video. Thank you guys for watching, and I hope to see you in the next video.